on this computer. We can see. Yeah, I know. It's you don't want to see my face. Anyway, I'm in my son's bedroom. I'm under his bed actually. That's why there is not much light. But you're not here to see my face anyway, so that's fine. Okay. Share the screen. This one is going to go there, there, and there. Can you see the first slide with the title slide? Yeah? Can I get a yes, please?
Yes.
Yes, yes.
Thank you very much. Okay, so let's resume the course again. Apologies for the delay, the 15-minute delay. Okay, so multi-state models. So these models, I mentioned that already this morning, these are an extension of the Cormack-Jolly-Seber model we've seen previously this morning. So in multi-state models, what we have is we have a state that refers to an individual and time-dependent covariate, which is categorical. So individual, time-specific, and discrete covariate. Okay. By categorical, I mean that this variable takes discrete values. Okay, possibly different from one occasion to the other. That's the time-specific. Okay. So here an example of a multi-state data set. So we have 6 individuals here, and they have been monitored from 92 to 99. Okay, and individual 1, for example, was first encountered in 93, and in state or site or state 1, and then we recaptured in 94 in state 2, and so on. Okay. So it's basically the same data as before, except that now we record the state in which you've been recaptured. Okay, examples of states are sites, for example. I mean geographical locations, and we might be interested in estimating dispersal between these sites, right? Another example might be breeding status, and we might be interested in accession to reproduction or in assessing survival reproduction trade-offs in evolutionary ecology, okay? Another example might be disease status, and you could be interested in estimating infection and recovery rates, okay? So these multi-state models are very, very, as we will see, flexible, but they allow you to tackle a bunch of ecological questions, and they are very, very, very well, fun to use, as we will see. Okay, before we jump into the details, a bit of history. I like history. The first mention of a generalization of the Cormack-Jolly-Seber model dates back to several papers by Neil Arnason, this guy here, in the 70s. And but his model, Arnason's models, were not used before this paper by Arnason-Schwarz 20 years later, after Neil published his papers, 2 or 3 papers in the 70s. I believe Carl was a Neil PhD student. So this is why the generalization of the Cormack-Jolly-Seber model is called the Arnason-Schwarz model. And because also male scientists love to name models with their own names, I guess. Anyway, both Arnason and Schwarz were from the University of Manitoba in Canada. And I guess we need to thank Canada for multi-state model. Thank you, Canada. And this is my job for the day. Okay, before I get yelled out by this guy, I should mention that America too did great contributions to the field. Bigger, better, and stronger contribution, of course. Huh? And in particular, the main contribution was to realize that in the Arnason-Schwarz model, the sites or geographical locations could be actually replaced by any discrete individual states, like body mass in this paper here, or breeding states, like in this paper. And folks from the Patuxent Research Center that Marc mentioned in the very first lecture, like Jim Nichols and Jim Hines. The Jims were instrumental to these developments. Okay, like we did for the CGS model, we will use a state space formulation for multi-state models. Again, we have two processes, okay, that give rise to the observation we make on the field. We collect the data we collect on the field. First, the data you wish you had. This is the state process. So this is the data you get if everything was perfect and no detection issues or whatever. But now, in addition to being alive, you have the location where the individual was alive, okay? Say site A or site B. So in this example, the individual is alive in site A, then moves to site B, stays there for one occasion, and moves back to site A, and then stays for another occasion, then it dies, and remains of course, dead for the rest of the study. And again, like in the Cormack-Jolly-Seber model, we have stochastic arrows and stochastic links here with the dashed lines, and we have deterministic links with those solid arrows here. Okay, so when you're dead, you stay dead for sure, and to go from one state to the other, you're going to have to use a statistical distribution to decide where you are the next occasion. Okay, so that's the stochasticity. Okay, from the state process, we get the observation process, and the individual may be seen in site A, or seen in site B, or not seen at all. Okay, and the detections are conditional on the state. So the detections are conditional on the upper layer here, the state process. Okay, for example, at occasion 2, we are alive inside B. Okay, so you may be detected or undetected. It happens that here the individual was detected in site B, given that he was alive at site B at the same occasion. Okay, at the next occasion, it's still alive in site B. It remained inside B, and it is not detected. Okay, and when you're dead, of course, the only option you have is to be undetected, to get non-detected with probability 1. Okay, of course. And at first encounter, the first occasion of capture of encounter here, you're alive for sure. So the link is deterministic, and you're seen in the state where you were alive, of course. Okay, you cannot be seen in the other state, in other sites. Sorry, right? Okay, to build a model, we need some quantities, some parameters we need to define. So we're going to write down the state process with this parameter here, this big phi, which is the probability of being in state y at t plus 1, given that you were in state x at t, okay, at the beginning of the interval, right? So it's kind of generalizes the survival probability. But as we will see in a few slides, this parameter includes two processes, the survival and the fact that you move or not from one side to the other, okay? So for now, this parameter includes both processes. We will see how to split that in two in a minute, right? So this generalizes the survival, and we put everything in a matrix, okay, where we have in rows or a table. And if you don't like the term matrix, use tables, that's the same thing. So we have in rows, we have the sites, okay, site A, site B, and the state dead at time t. And in columns, you have the states at time t plus 1, right? So again, site A, site B, and dead. Okay, so you go from site t in rows to site, you go from occasion of time t in rows to occasion t plus 1 in columns, right? This is important that you keep that in mind, because we will use that all the time from now on. Okay? It's the same thing as before. Huh? It's just that we have this dead state here, and the other constraint we have is that the rows, the probabilities in a row should sum up to 1. Okay, so this one plus this one plus this one should sum up to 1, and it's okay, right? And of course, we find again that if you're dead at time t, then the probability that you are alive in site A or B is 0, and you for sure you remain dead at occasion t plus 1, right? Okay. And for the observation process, we will need well, the detection probabilities, and we'll put them in a matrix as well. The only thing you need to notice is that now we have the observations in columns, and we have the states at time t. So it's the same time where you do the observation at time t as well. So you have the states in rows here. So you are alive in site A, B, or you're dead. And then conditional on those states, you do the observation. So you can you are seen at site A with probability PA, or you're seen at site B with probability PB, given that you are alive in site B, or you're not detected, given that you're alive in site A with probability 1 minus PA, or given that you are alive in site B with probability 1 minus PV, or if you're dead, well, the only option you have is to get undetected with probability 1. Does that make sense? We have everything in tables or matrices for convenience, and then we will use these matrices to, of course, I take some time to introduce that, but because we will use those matrices later on to implement this model in Jags. Okay. So now let's say we have an individual encountered at some occasion, T, here, in site A. What are the probabilities that this individual will be in site A, alive in site A, in site B, or dead at the next occasion? To compute, to calculate these probabilities, to write down those probabilities, we need to define this quantity Z. It's the same thing as before in the Cormack-Jolly-Seber model, except that now we extend, it's the latent state for being alive or dead, except that now we need to extend this definition to several sites. Okay, so ZIT is the state of individual I at time t. It's going to be, let's say, 1 if the individual is alive in site A. It's going to be 2 if the individual is alive at time t in site B, or 3 if the individual is dead, right? So instead of being just 0, 1 or 1, 2, like before, a binary random variable, it's a random variable that takes several values, okay, more than 2. And it's latent, as before, because we know its values only when individuals are seen or detected. Otherwise, you don't know whether an individual was alive or dead when it gets undetected. Okay, then once you know the state at t, to get the probabilities of being in either state at t plus 1, well, you're going to use the matrix we've introduced before. And this matrix, remember, it gives you the states at t plus 1, given the states at t. So here we know the state at t. It was the individual was alive in site A. So we're going to pick the probabilities in row 1, the row corresponding to site A. And the probability of being in site A at t plus 1 is going to be this probability, and then site B this probability, or you could end up dead at t plus 1, given that you were in site A at t, with this probability here. So you see how useful this matrix is, because conditional on the state at t, you can get the probabilities of being in any state at t plus 1 by just picking the relevant row in this matrix, okay? Knowing the state at the previous time. And so if you formalize that, if you generalize that to any time, any occasion, and any individual, we're going to say that the state of an individual I at t plus 1 is distributed as a categorical distribution, dcat, in Jags, with parameter this row ZIT, which is the state of the same individual I, but at the previous occasion, T, of the matrix omega. Matrix omega is the matrix where you stored all the big phi parameters, right? So again, you just say, okay, in which state was I at time T? If I was dead, then the probability of being in site A, B, and dead at time T plus 1 is given by this vector here, 0, 0, 0, 1, right? And so this dcat distribution, the categorical distribution, it's nothing more than a multinomial distribution with a single trial. Okay, so we get 1, 2, or 3. Okay? It's the 3 faces of a dice with only 3 faces, 1, 2, or 3, and alive inside A, alive inside B, or dead, right? And this distribution takes as a argument a vector of probabilities for each category. So it's a row of this big matrix here. And to decide which row we take, we just have to know the site at the previous occasion, the state, sorry, at the previous occasion. Okay, for the observation process, let's say that our individual was alive inside B. Then we will need to define observation, the observation of this site I at time this individual I at time T. So it's going to be seen in site A with some probability, and Y will take value 1, for example, or this seen detected in site B, it will take value 2, or not seen, it will take value 3. So that's all the values that Y can take, 1, 2, or 3, 1, 2 if seen inside A, 2 if seen inside B, and 3 if dead. If non-detected, sorry. It's not state, it's the observation process here. So the Y, okay? And then given that you are alive at time T, here inside B, you have several options, but you don't have so many options. You cannot be detected inside A because you are alive inside B. So the only option is to be either detected inside B with some probability, the probability of being inside B, the probability of detection and alive inside B, or not being detected here. And to formalize that, again, we're going to use the matrix we introduced before, the big theta matrix, which is the observation matrix, where we have the states in rows and the observations in columns. So in our example, we are alive at time T inside B. So this is the second row of this matrix here. And so we get the observation at time T, the same time as the state at which we give the state here. It's not conditional on the previous occasion. You do the observation at the same time you get the state of your individual. It's conditional on the state at the same occasion, and so you are the observation of individual I at time T is given by the probability of being observed, detected, is given by this vector here. So it's again a categorical distribution in Jags with probability, the rows of this matrix of observation here, conditional on the states at the same occasion, right? Okay, it will make more sense when we get to the example and we see several alternative formulation and everything. Okay, so the first time you see that, it takes some time to get familiar with it, but then you'll see that it's very powerful to express that as a matrix, a transition matrix, a state matrix, and an observation matrix to be able to write down the model very conveniently and not having to describe all the probabilities and everything. Okay, I mentioned that this parameter, big phi here, this is the probability of being in state Y at t plus 1, of ending up in state Y at t plus 1, given that you were present, you were in state X at time t. And I said, okay, this parameter, it combines two processes, two ecological processes, the survival and the fact that you remain on the same site, or you make a move from one side to the other, or you just die. Okay. So we're going to distinguish the two processes: the survival, which we will denote phi x, which is the probability to survive on the interval t plus 1, given that you were in state x at the beginning of the interval at time t. Okay. So this is the same thing, the same survival as in the Cormack-Jolly-Seber model, except that now we need to know to decide the state of the individual. Okay. And we're gonna, by convention, we're gonna say, okay, that was the state at the beginning of the interval. In which state you were at the beginning of the interval, and then the new parameters are the transition parameters, or the psi, the probability to move from state x to state y over the interval t plus 1. Okay, so t is for t plus 1. So the survival acts on the time and acts on the time interval between t and t plus 1, and same thing for the transition. You make the move, or you stay on the same side between t and t plus 1. Okay, and so you go from state x to state y, and y can be x. Huh? You can remain on you may totally it's totally fine to remain on the same side, or not to move from one state to the other. Just stay in the same state. Okay, so the same matrix here can be written again as this one. So this probability, which was the probability of being inside or state A at t plus 1, given that you were in state A at t, it's the probability of surviving in the state A over the interval, and not to move from A to B. So 1 minus psi. The probability of being in site B at t plus 1, given you were in site A at t, it's the probability of surviving over the interval in site A times the probability of moving from A to B. And then the probability of going from site of being dead at t plus 1, given you were in site A at t, it's just the mortality probability, 1 minus phi A, right? And you can do the same for being alive in site B at t and being dead at t. The cool thing by doing that, by splitting this big phi in survival and transition, is that we make explicit survival and transition between states, which makes it easier to test different effects on survival and transition probabilities. Whereas when you write down the model with this parameterization here, you cannot really split survival and transition from each other. You cannot really distinguish one from the other, which makes it difficult to have different effects on survival and transition probabilities. Okay, some code, and then we'll see some examples. Okay. Again, implementation in Jags. We start with a loop. We start with the likelihood, as usual, and we start with a loop over the individual. So you have your table of individuals, your data set of individuals, and you go through one after the other. So that's what this loop does, right? Like in the Cormack-Jolly-Seber model, we start by kind of getting rid of what happens at the first encounter. So at the first encounter, so that's the state of your individual I at first encounter. Remember the F, which gives you the date of first encounter, the occasion of first encounter. So in the Cormack-Jolly-Seber model, it was always 1, because when you are detected, for sure you are alive. Okay, when you are first detected, you are alive. In our case here, when you are first detected, you are alive. There's no doubt about that. There's no problem about that. But you are alive in one state or the other, and this state is given by the observation, actually, by the Y, by the observation in which you've been detected. Okay. Is there a question or no? Because there is some noise. Can you turn off your mics, please?
I just take the opportunity to ask a question.
Go ahead. Go ahead.
In the previous slide, you presented so in the matrix the combination of survival and transition probabilities. And I remember from eSearch you can develop separate matrices to present survival and transitions. The use of that is especially to, for example, then consider the transitions and then the survival. For example, there's transition from A to B and then survival in B. Is it possible also to do that with Jags? Because
of course.
When I developed the transition, the survival matrix in Jags, it's just one and only single matrix for transition and survival. So
yeah, but still, okay, you have one matrix, but still you can have a different effect on survival and the transition probabilities. It's not a problem. You don't have to write down the product of the two matrices. That's okay.
Okay.
Okay. So we'll see an example in the practicals. No worries about that.
Okay, great. Thanks.
Okay. So we've okay. So we've started the case is now. We've done that for the first encounter. It's going to be just the observation in which state you were observed at the first encounter, right? So either in site A or site B, you can be dead, so it's never going to be 3, the observation dead, non-detection. Sorry. Okay, so then we go through time. So after the first encounter, we say, okay, let's make a loop from the occasion right after the first occasion, f+1, up to the last occasion of your data set, right? And then, well, we're just going to take these equations here, the categorical distribution for the state process and the observation process. Sorry, I hate when people do that in presentation, like going through slides very quickly. And I'm doing just that. And the state process, okay, so you remember the state of your individual I at time t is given by, you pick that in a categorical distribution, which is just a multinomial distribution with one trial. And what you need is to specify the parameters of this DCAT distribution. And it takes just a vector of parameters, of probabilities. So the vector of probabilities, like I said before, it's a row of the transition matrix of the big phi matrix. Remember, we did that and say, okay, that's the first row or the second row, I can't remember. And so this is what I am doing here. This PS here is just the big phi matrix, okay? The one with hang on. That's this matrix, right? This omega matrix. I call it omega or big phi, whatever. And so we're going to pick a row in this matrix, and that's going to be the vector of our categorical distribution. And which row? The row given by the state at the previous occasion. So it's the Z at time t-1. Okay. So if it was alive in site A, it's going to be the first row. So it's going to pick the first row in this matrix PS that we will build in a minute. Next slide. And this matrix can be individual specific, time specific, and then here I don't write it, but I shouldn't do that. I should write that, yeah. Here, the fourth dimension of this matrix is just 1 up to 3. It picks the 3 columns corresponding to the first row of or the zth row of matrix PS. And same thing for observation. Now at the same occasion, the Y are the detection and no detection we're making in each site. So Y takes value 1 if you are detected in site 1, 2 if you are detected in site B. I said site 1, site A. 2 if you're detected in site B, and 3 if you're not detected, right? And so these values are taken in the categorical distribution with probabilities, with vector of probabilities, a row of the observation matrix, PO here. PO was B, or what was its name before? Oh, theta, big theta. Okay, so PO is big theta, and we take the row corresponding to the state of the individual I at the same occasion T. And again, Z may be individual specific, time specific, and then you take the 3 columns here. It's 1 up to 3. That's the fourth dimension here. So how do we build these matrices? Oops, sorry. And again, it's the same idea as in the Cormack-Jolly-Seber model. You go through the individual and time, and you write your parameters, your matrix of parameters here, PS and PO, as generally as possible. So they are individual and time dependent. Okay, these matrices, PS. So we have 4 dimensions. The state, for example, for PS, which is the matrix of transition, you have the first dimension here. It's for the state at t+1. Then you have the individual dimension, then the time dimension, and the fourth dimension is the state at t+1. And for the observation matrix, you have the state at t. Okay, you have the individual dimension, the time dimension, and the fourth dimension is the state. The observation at t that you make. So it's very general, and from there you can obtain simpler models. Okay, how do we define the state transition and observation matrices, the big theta and the big omega or phi matrices? Again, we want to have them very general, so we go through a loop on individual and a loop on occasion, and we say, okay, PS, which is this matrix, you remember this matrix here, which gives you the probability of being in state Y at time t+1, given that you were in state X at t. And here we split survival, and we split this big probability into the survival and the transition. So PS has 4 dimensions, as I just said. The first dimension is for the state at t+1, at the first occasion, at the occasion t in rows, right? And the fourth dimension here, it's the columns. It's the state at t+1. It's the state where you go. Okay? And then we also have those 2 dimensions, individual and time here. You could get rid of the individual and time dimension if you didn't have any time or individual effect on your survival or transition parameters. But for now, let's go very general, and from there we will apply constraints on this model to build simpler models. So this big theta, this big omega or phi matrix, we fill it in by hand. We say, okay, the first cell here of this matrix, it's being inside A at t+1, given that you were alive inside A at t. Okay, that's the definition of this cell here, and it's just the product of phi A times 1 minus the probability of moving to B. And same thing for this probability here. It's this cell, and this one. It's still for the state A here, the first row, and that's the third column. So that's this parameter, and so on. And so by doing that, you define this matrix, this big matrix here, from which you will pick the probabilities that you will use in the categorical distribution for the state process. And you do the same thing for the observation matrix. So you remember you have this matrix here, this observation matrix, the big theta, and you build it by hand in Jags, and you define PO with 4 dimensions, the state in the first dimension, the observation at the same occasion in the fourth dimension, and then you have the second and third dimensions, which are the individual and time dimension, and then you write down this, you build this matrix by hand, and you say, okay, you have PA, PB, and you just write down that. And here we say, okay, we want to have the survival and the transition parameters time dependent, right? So we don't have an I index in the survival or in the transition parameters, but we could eventually have it. We could totally have it. Okay. And then from this very general model where your parameters are individual and time specific, let's say we want to have a model where survival is just it's not constant anymore as in the Cormack-Jolly-Seber model, but it's state specific. So we have a survival for being alive for site A and another survival for site B. We estimate the probability of moving from A to B and moving from B to A. Okay. And we have a detection probability that is different from one site from site A to site B, right? So we have some site-specific heterogeneity or state-specific heterogeneity in the detection process. So that's one way to account for heterogeneity in the detection process, to have site-specific detection probabilities. And then we use the same trick as in the Cormack-Jolly-Seber model. We say, well, our very general parameter, phi, the survival in site A, which was time dependent, we say, well, now it's just one parameter, mean phi, and the detection, the survival probability in site B, which was time specific, we just say, okay, we don't want it to be time specific. We want just a state effect, a site effect. So it's one parameter, but it's not the same as in site A. It's going to be another parameter. Okay, so we have two survival parameters different from one site to the other. We estimate the two movement parameters or dispersion, or depending on each site or state, or transition probabilities. That's the most general term, transition probability from site A or state A to B. Okay, and we say, well, we don't want it to be time dependent, just use a constant, mean psi. And of course, there is no reason to believe that the transition from A to B is the same than the one from B to A. So we say it's another parameter, mean psi 2, right? And then same thing for the detection probability. We have two parameters, mean P1 and mean P2. And then we just need to specify the priors, and we're done. So the priors, we're going to use, well, that's a bit too much, but we're going to use a loop of from 1 to 2, and we say mean phi, it's 1 and 2 are uniform, have a uniform distribution priors. Same thing for psi and same thing for p. We don't have any link function here because we use constant parameters, and for constant parameters, the uniform distribution is doing the job of constraining the parameter to be estimated between 0 and 1. It's the domain of definition of the uniform distribution is between 0 and 1. So we don't have any problem of constraining the probabilities here, survival, detection, and transition to be between 0 and 1. The prior is doing the job for us, right? Okay, to sum up, we have those three components: the likelihood, the definition of the transition and observation matrices, and the priors and constraints. So basically, the likelihood will not change from one model to the other. You will use exactly the same likelihood because it's general enough for you to be able to fit any models. And your job is just to make sure that you have the right transition and observation matrices that fit to your purpose, and to apply the constraints that you want to have time effect, individual effect, random effects, or whatever, like we did for the Cormack-Jolly-Seber model, right? It's a bit more complex because, well, we generalize to several states. Huh? Okay, so planning before I jump into the live demonstration, do you have any questions? Again, it's these models are more complex than the Cormack-Jolly-Seber model. So at the first time you see them, it's not easy to grab all the complexities and all the subtleties of the model, but it will come for sure. Okay, if there is no question, a quick demonstration of the model I just presented. Okay. Can you see the panel of my RStudio? Yeah, correct?
Oui, yes.
Merci. Thank you very much. So I load Jags UI, sorry. UI. I don't need to specify a path in my case because I'm using RStudio project, so everything is taken care of for me. I'm gonna read a file with multi-state data. You have the file in the directory called dat in the Dropbox repository. So obviously it doesn't work. It doesn't find the file. Why? Because I didn't open the project. I opened the file directly, so it cannot find the path. Okay, so I'm doing it again. Right, and this is not the script I want. I want the multi-state. Here we go. Okay, clack, clack, clack. Jags UI, Jags UI, and we read the data. Now we can read them. Okay, I'm gonna make it matrix and print it. You see that you have, for example, this individual, the 140, it was first captured at occasion 2 and in site 1, and then recaptured at the next occasion in site 2, then missed the next 2 times, and then at the last occasion of your study, it was recaptured in site 1 or state 1, whatever these codes mean. Actually, the model doesn't really see whether it's a breeding state or disease states or site or whatever. It's just 1 and 2s and zeros for the model, right? It's up to you to define what these states mean. Okay, we have 800 individuals and 6 capture occasions. Right. Okay. So we have 2 sites, blah, blah, blah. So this is what I just said, right? The Jags code. Okay, the Jags code. So we are in the model, and it's always good practice to define in the script, in your code, what the parameters of your model are, okay? It's very good practice. So it's boring because you have to do that, you have to write many things, blah, blah, blah. And this sign is for comments, like in R. It works for Jags too. Again, it's very good practice to define the parameters you use in your model in your script. You will say thank you to yourself in 6 months of time when you have to reuse the same model, but you don't remember anything about multi-state models or whatever. Okay, so the parameters: survival in each site, the transition or movement or dispersal or whatever, infection rate or from one site to the other, the detection probability in site A and B, and then the states are, we have 3 states. So it's very, very, very important to also, before you start building your model, define the states and the observations. It will help you a lot to build the matrices of observations and transitions, okay? So the states are alive in site A, B, or dead, and the observations. So make sure that you really distinguish observations, what you see, from the states, what you wish you'd be able to see, okay? So the true states of the individuals. Detected or seen or recited at A, B, so this is a 2, or you're not detected, it's a 3. And you don't know whether you're dead or not. That's why it's hidden or latent state, the Z. Okay, oh, we start with the priors, why not? The priors are just uniform distribution between 0 and 1s. And then we write down the matrices. So this is the transition matrix. So first dimension is for the state at T. And, okay. It's a bit different from the lecture. Because I wanted to fit a model with constant parameter, I didn't need to have, okay, I did something a bit different from the lecture. Anyway, I'm going to explain you why. Okay, in the lecture, I had this PS matrix, which had 4 dimensions, remember? State at occasion T, individual, time, and state occasion T+1. occasion. The thing is that when you do that in Jags, you have an object with 4 dimensions, and you do the MCMC stuff and blah blah blah. So it's in terms of memory storage and usage. For Jags, it's very demanding because it has to carry out with these huge matrices or arrays with 4 dimensions, and this is for transition. And you have the same thing for the detection matrix, for the observation matrix. So in that specific example, where I just wanted to have constant parameters, I have just and also you had the 2 loops, individual and occasion, to define those transition and observation matrices. In that case, to make the code faster and the fitting process a bit faster, I've simplified everything. I just got rid of the loops and the 2 dimensions for individual and time, and I said, okay, I have just a 3x3 matrix. It's not an array with 4 dimensions. It's a 3x3 matrix with state at t in rows and state at t+1 in columns. And this is given by my matrix as the transition matrix we saw in the lecture, right? And then for the observation matrix, it's the same thing. I got rid of the double loops and the dimension I and j. Individual and time, so that Jags doesn't have to carry out with those huge transition and observation matrices. Okay, so by doing that, I'm losing all the cool thing with the general model, where I just have to apply constraints to get simpler models. Okay, with this kind of what I'm doing here is very specific to the model with constant parameters. If I want to go for another model where I have an individual effect or time effect, I will have to go back to what I show you in the lecture, of course, right? And the likelihood, that's the one we saw in the lecture. What happens at first encounter, and then state process and observation process. So the Y are the observations. So we just we pass that in R. We have the same function to calculate the date of first encounter, the occasion of first encounter. And if you have a look to F, F is just for each individual at which occasion it was first encountered, right? Okay, so my data are 0s, 1s, and 2s. But remember, in the state space model, what we need for Y, for the observations, we need 1, 2, and 3. Okay, 1 for detected in site A, 2 for detected in site B, and 3 for non-detected, not seen. So I'm going to do some recoding here. I'm calling RCH the recoded capture history dataset. And I say, okay, everywhere you see, anytime you see a 0, a non-detected, you recode it as a 3 for non-detected in the state space model. Okay? So now RCH, there is no 0s anymore. All the 0s have been replaced by a 3 for non-detected. Okay, so that's the Y here in the code, right? Data, that's no difference with the Cormack-Jolly-Seber code. The data, the first encounters, number of occasions, number of individuals. Then we need some initial values for the states, but the states are no longer just 1 or 2 for alive or dead. We have alive in site A, or alive in site B. Okay, so it's a bit more involved, but you have the function to generate those initial values, so it shouldn't be difficult. And then we put that in a function for initial values. You see that for all the other demographic, the survival, transition, and detection parameters, we pick an initial value in a uniform distribution at random. Okay? So it will change every time you run the model again. It will change initial values and the parameters to monitor. I'm doing just a very few iterations just to show you that it works. And then it's in parallel, so we don't have anything. We don't have the progress bar here. But it shouldn't take too much time. I think it's quick in general, and it's faster because okay, so it's done. Okay, so hang on, and then we'll take a break. Okay, so the results: survival. So you see the mean survival for each site, A and B. You have the transition from site A to B. around 30%. So the probability of going to B, given that you are in A, it's 30%. So there are more chances to actually remain in A, and the transition from B to A is around 60%. So yeah, you tend to leave B to go to A. And the detection probability is higher inside A than inside B, around 75% against 37%. Okay. You can have a look to the trace plot. There are a few things we can do, right? Let me show you that. Hang on. It doesn't work because here we go. So these are the trace plots for survival inside A, side B, the transition probabilities, and you see that we need more iterations. Okay, right? It takes some time to reach the stationary distribution of the Markov chain. But anyway, I just run it for I don't know 400 iterations. It's nothing. So here I run it for longer. So it's long, but it takes less time than if you had coded the model with the 2 dimensions for the observation and transition matrices. Okay, so that's a simplification of the model. If you have to fit a model with only constant parameters, you don't need to. For multi-state model and for single site for Cormack-Jolly-Seber models, it doesn't really matter. You will go. I mean, you get results very fast. So, okay. Do you have any questions before we take a break? I see that there are some questions in the chat. Yeah. Everything we've seen this morning, effect of covariance, random effects, either individual random effects or temporal random effects or whatever. I mean, you can do exactly the same thing in the multi-state setting. It's just that your data is a bit different, but the parameters have the same meaning. It's survival, and you have an extra parameter with the transition probabilities from one site or state to the other. But you can do exactly the same thing in the GLM-like philosophy. So you have your parameter, survival or transition or detection, which is written as a linear function of your covariance or your random effect on some link, on the scale of some link functions. Okay, a logit or whatever. Right? Okay, let's take a break then. It is, okay, 20 to 3. So let's say 5 to 3. We regroup at 2:55 to be precise. Okay, in 15 minutes. Great. Okay.